in such a nice conference. So I'm going to talk about what I call tetrahedron duality. This is based on my work, which is going to be published soon. But this is based on previous works on which I mentioned more. Okay. Yeah, so let me start. Well, first of all, is this visible? So first of all, let me start with motivation. Why I would like to talk about this stuff at all. So the main goal is to understand connections between gauge theories and integrable systems. Okay? So many of you are actually interested in either gauge theories or either integrable systems or both. So I think this is a good topic. And in this context, connections between integrability and gauge theories, actually integrability has been found to appear in many different gauge theory contexts. And I have listed some of well-known such context instances. One is what's called gauge beta correspondence, introduced by and worked on by many people, including Nekrasov-Shashvili. And the second one is actually related to this talk, which is called gauge YBE correspondence. So I will talk more about this later. And also more recent stuff is something called 4D transcend theory, which is a four-dimensional analog of three-dimensional transcend theory. And then you can construct many integrable systems, like integrable lattice models, as well as integrable field theories using this four-dimensional transcend theory. I'm not going to talk about this. And last but not least, there is a huge amount of literature on what's called ADS-CFT integrability. I have nothing to say about the last point. But you notice that for all of these instances, relevant integrable systems are all two-dimensional. And natural question is, what about three-dimensional integrable systems? Are they related in any way, like similar to these two gauge theories? So that's the main question I would like to answer. I will give one answer to this question. So as you see, well, the number of pages, number of slides is small. So please stop me at any moment and ask me questions as much as you want. Otherwise, you'll have to wait so long to attend the ceremony. All right. So let me first review a little bit about the Yang-Baxter equation, which is a fundamental relation for the integrability of two-dimensional systems. So I'm going to explain the case of two-dimensional classical spin model in statistical mechanics on a square lattice. So here in this picture, I have drawn a 2x3 square lattice on a torus. And each line comprising this square lattice, they are oriented. And then you have periodic boundary conditions, okay, in the horizontal and vertical directions. And I have these circles. These circles are spins or spin variables, so they can take different values. And then I number these lines 1, 2, 3, 4, 5. We have 5 lines, and to each line, to the 8th line, well, let's call it LA, there is an associated continuous parameter RA, which is called the spectral parameter for that line. Now, let's look at one of these vertices, intersections of two lines. Let's look at, for example, here. Okay, locally, it's you have a crossing of two lines surrounded by 4 spins. And let's say that 4 spins, let's say that they can take n different values, from 1 to big N. And let's say that they take values I, j, k, l like this. Now, so these 4 vertices in the kind of model I'm considering, they interact around the vertex. So there's an interaction energy associated to that interaction, and I call it E ijkl, which also is a function of these spectral parameters R1, R2. So I'm going to consider this kind of statistical mechanics model. And this kind of model is called the vertex model because interaction takes place at a vertex. So, so this is a general statistical mechanics model. Now, what I'm going to do is the following. So instead of considering spin variables taking n different values, I assign to each line LA an n-dimensional vector space VA. And then I define an operator, which is called R matrix, to each crossing of two lines. If two lines are LA and LB cross, then there is an associated operator R matrix RAB, which is also a function of these spectral parameters. Sorry, this should be read RA and RB. And this is an endomorphism of VA tensor VB, which means that this R matrix has 4 indices, 2 on bottom, 2 on top. And then the definition of this R matrix is very simple. RAB, or R matrix element ij, comma KL, is simply defined by the Boltzmann weight for the local interaction energy for spin variables ij, KL. So I can define this operator acting on this tensor product space. Now suppose that this operator R satisfies the famous Yang-Baxter equation. So this is a Yang-Baxter equation. And then the model is, you can show that the model is integrable in a certain technical sense. And if you're smart enough, probably you can use this integrability to solve for, say, the partition function and leave cover. So what is this Yang-Baxter equation? Well, Yang-Baxter equation takes this form. Okay. First of all, how to read this? What is R12? So first of all, each side of the equation is actually an operator acting on B1 tensor B2 tensor B3, and R12 acts on B1 tensor B2 by this operator R matrix. R23 similarly acts on B2 tensor B3 by this R matrix, but it acts by identity on B1, and so on and so forth. And there's a visual, famous visual presentation of the Yang-Baxter equation, which looks like this. So you have 3 oriented lines on the left-hand side, and then you have line number 1 going from the bottom left to top right, and line number 2 going to the right horizontally, and then crossing between line number 1 and line number 2, there's an associated R matrix R12. Okay. And then if you follow the path, then next you reach this point, which is crossing of line number 1 and line number 3, to which we assign the R matrix R13, which is the second factor on the left-hand side. And finally, you have crossing of lines number 2 and 3, to which you assign R23. So this picture represents the left-hand side of the Yang-Baxter equation. Okay. So what Yang-Baxter equation says is that if you take any one of 3 lines, let's say horizontal line, you move it upward so that the horizontal line crosses the intersection of the other 2 lines, then you end up getting the right-hand side, this picture. So these are topologically distinct configurations of 3 intersecting lines, but Yang-Baxter equation says physically they are the same. If you calculate any quantity on lattice containing this portion and another lattice which differs from the same of this lattice by this local move, then the partition function is precise. Okay, so that's the context of the Yang-Baxter equation, and this equation implies integrability. Now, if you count the number of degrees of freedom and the number of components of the Yang-Baxter equation, you quickly realize that the Yang-Baxter equation is really hard to solve because it's a hugely overdetermined system of equations. So R has n to the power 4 components, whereas Yang-Baxter equation itself has n to the 6 components. So it's kind of a miracle that there are any non-trivial solutions. But there are, and there are interesting solutions. One famous example is something called the 8-vertex model, which is actually equivalent to one-dimensional XYZ quantum string chain. So there are many interesting solutions, and there is actually a powerful mathematical machinery behind the construction of these solutions, which are known as quantum grids. So this is something we know. from two-dimensional integrability. Okay? Yeah. Now, what about 3D? So we want to upgrade everything from 2D to 3D, right? So we want to consider, instead of two-dimensional square lattice, three-dimensional cubic lattice. Now, if you imagine cubic lattice in your head, what are they consisting of? So they consist of intersecting planes. Okay? So you have many planes intersecting orthogonally, and that makes a cubic lattice. Can you imagine that? So this is a local picture of three intersecting planes, plane A, plane B, and plane C. And then their intersections make this kind of line, intersection lines. And this is a local picture of three-dimensional cubic lattice around a vertex. Okay? So in this case, we can also assign spin variables, place spin variables on the edges of these thick oriented lines. Okay. And let's say that, so maybe I should, well, let's say that you have spin variables on this edge and its value is I. You have spin variable on this edge, its value is J, and spin variable on this edge, its value is K, and so on and so forth. So around each vertex of this cubic lattice, okay, made by these oriented black lines, you have 6 spin variables surrounding the vertex. And there's an associated interaction energy as well. And you can define this R matrix by saying that matrix element of this operator, which now acts on the tensor product of 3 spaces, is simply given by the Boltzmann weight for this configuration of spin variable. So you can define this operator, which is called R matrix again. So very similar to the Yang-Baxter equation case, you can introduce the R matrix in this kind of model. Now, what replaces the Yang-Baxter equation in the case of 3D is called the Zamolodchikov's tetrahedron equation. So Yang-Baxter equation was R equals R, that kind of equation. Tetrahedron equation now has, each side of the equation has 4 factors of R matrix. But again, of course, no one can remember this, right? This is too complicated to remember, but we also have a visual presentation of this equation. Now, what you have to imagine is that here, you actually have 4 intersecting planes, and they together bind a tetrahedron, which is this region. Okay? So you have 1 plane horizontally and 3 planes like diagonally, and they bind this tetrahedron. And to each intersection of 3 planes, 3 out of 4 planes, for example, here, this is the intersection of plane number 1, plane number 2, plane number 4. You have an associated interaction, and energy and so on, associated R matrix. So this intersection point represents this operator R1, 2, 4, this factor, and so on and so forth. Okay. So now the tetrahedron equation says that this configuration of 4 intersecting planes is equivalent to this configuration of 4 intersecting planes. So again, you can take one of the 4 surfaces. Which one? It doesn't matter. Let's take this horizontal surface up here. You pull it down, all right, and then you end up getting this configuration of 4 surfaces, okay, 4 planes. And then tetrahedron equation says that if you calculate the partition function on a lattice which contains this local configuration, and then you change this local configuration to this local configuration, the partition function remains invariant. So this is the content of the tetrahedron equation, and this actually implies what we call integrability of this 3-dimensional spin model. So that's this is the tetrahedron equation. I quickly introduced it. Now, so all is very natural. It's a very natural generalization of the Yang-Baxter equation from 2D to 3D. Okay. It depends on your model. Yeah, so its dimension is the the number of different states each spin variable can take. So if your spin variable takes, say, spin up and down, then this each v is two-dimensional. Yeah, but I'm going to consider a model in which these are infinite dimensional. Now, am I doing with time? Good. Now, so all seems very good, except that the following. So tetrahedron equation, well, this slide, so I talked about tetrahedron equation last year, ICPS, and I used almost the same slide, and I didn't have to update except the last sentence because I'm going to talk about different content today, but all of these are exactly probably the same, except here, around here. But all right, so because things haven't changed much, so the tetrahedron equation actually has a relatively long history because it was introduced by Zamolodchikov in 1980, which is before BPZ paper on 2D CFT. Okay, that's a long time ago, but it's far less developed than Yang-Baxter equation. In fact, there's only one book on this subject written by Professor Kuniba from Tokyo, and that was published in 2022, 2 years ago. So why? Well, the reason being seems to be that the equation is very complicated. So now if you count the number of components, R, each R has n to the power 6 components, but the equation itself has n to the 12. Nevertheless, there are some interesting known solutions, and indeed, in the first two papers, seminal papers by Zamolodchikov, he wrote down first non-trivial solutions of the tetrahedron equation, which, according to Baxter, is by what appears to be an extraordinary feat of intuition. So it's kind of, he was just great, too great. Okay? But he didn't prove that these solutions really solve the equation. Later, Baxter proved that. But obviously, tetrahedron equation, in my opinion, is very important simply because we live in three-dimensional space. Okay? So it makes sense to focus a lot on three-dimensional statistical lattice model. Okay, we may be able to create such statistical lattice models in some materials. So why don't we study those? So we want to study those, but it's just too complicated. But I would like to stress that there has been some recent progress, especially regarding the connections between tetrahedron equation and supersymmetric gauge theories. So in my work with Xiaoyue Sun, who is sitting right here, and then follow-up work by Inoue-san, Kuniba-san, and Hiroshi-san from Japan. And then we also collaborated, and there are some related work on a different version of tetrahedron equation by these gentlemen. So solutions of tetrahedron equation have been constructed using some mathematical structure called quantum class algebras. And these solutions have been related to three-dimensional supersymmetric gauge theories. So precise relation is that matrix elements of these solutions, so R, solutions are called R, and R's are matrices. And matrix elements can be identified with partition functions of certain 3D gauge theories on S3 sphere. So there has been some recent progress which I consider interesting. But today I'm not going to talk about this because I have talked about this already many times. So I'm going to talk about the different construction of solutions of the tetrahedron equation, which I also consider is interesting, using infrared equivalence, duality of two-dimensional supersymmetric gauge theories. So this is what I'm going to talk about, and this is sort of the end of the introduction. So this is a good time for you to ask questions if you have any. Okay, so good. Okay, I have spent 20 minutes, which is okay. Now, so before talking about this construction of solutions of tetrahedron equation, let me talk about something called gauge YBE correspondence, because this was an important motivation for me to look at this project. So gauge YB corresponds, as the name suggests, is correspondence between supersymmetric gauge theories and solutions of the Yang-Baxter equation. So we are back in 2 dimensions again. So this gauge YB corresponds was found by actually, I think Yamazaki is one of the first people who found it. And I did some related work, which is directly related to my today's talk back in like almost 10 years ago. So what is this? So there are different versions of this corresponds, but let me consider the simplest one, which has its origin in brane construction of gauge theories. So I'm going to consider something called brane box model, which was introduced by Hanani Zaffarani in the late 90s. So I'm going to now 10 dimensions. I'm going to consider superstring theory, actually type 2B superstring theory. It's a 10-dimensional theory. Okay. So you have 10 directions from direction number 1 to from x0, x1, x2 up to x9. So these are coordinates. Okay. So but I divide the 10 directions like this. Yeah, this is R4. Yeah, I should have put 4 here. Yes, I was looking for some typos to fix yesterday, but I couldn't remember which part was wrong, and then this. All right, so this is R4. Right? R4, and then 0, 1, 2, 3 means that it has coordinates x0, 1, 2, 3, and so on. Okay. Now, superstring theory has extended objects, and in type 2B theory, there are 2 kinds of 6-dimensional objects, which are called D5 branes and NS5 branes. So what you do is you take big N number of D5 branes and let them extend in these directions, R4, so this 2 is really 4, R4 cross R2 for 5 directions. And they sit at the origins of the remaining plane, 2 planes. Now you have stack of ND5 branes, but now I introduce NS5 branes in different directions, and to distinguish them, I label them with X, either XL, where L runs over integers, or YM, M runs over integers. So they are word volumes, so they extend in these directions. So these are the submanifold supports of these branes. Okay. So they all wrap R4 directions. And then, but NS5XL has coordinate, which is X4 coordinate, which is equal to L plus 1/2. So its X4 coordinate is fixed, but it extends in the X5 direction. Okay. And then X6 direction is fixed to the origin, but it extends in the X7 direction. So in total, there are 6 directions in which this NS5 brane extends. And similarly, I introduce NS5 YM, these branes, they extend in orthogonal directions. But if you imagine what's happening here, well, you can just focus on this part to 4, 5 directions. So this is just a plane, and on the plane you have stack of ND5 branes, and then you have NS5X planes. They are like intersecting this plane like this direction, NS5Y plane branes intersecting in these directions, and intersections form just a square lattice in the R2, 4, 5 direction. Is that okay? Yeah. So you get a lattice naturally. Now, what this does is that if you consider low energy dynamics of these D5 branes, then you find that its dynamics is captured by 4-dimensional quantum field theory, which emerges on R4 direction, R4 0, 1, 2, 3 direction. And this is a way to construct 4-dimensional gauge theory. Actually, it has n equals 1 supersymmetry. And its matter content, its gauge and matter content can be conveniently denoted, encoded in this kind of directed graph, which is called a quiver. So you may or may not have seen this kind of quiver, but let me explain what I mean by this. Okay. So what I mean by this is the following. So each vertex of this graph quiver represents, sorry, brain box model. Yeah, the name. This one? It's just, yeah, I'm going to explain. All right, so these vertices, so you can imagine this quiver is drawn on this R245 direction. Okay, you have a plane, you have a quiver on that plane, which looks like this. And each vertex represents SUN gauge group in the emerging four-dimensional gauge theory. And each arrow between two vertices represents a matter field, more precisely, which is called chiral multiplet. But it's a matter field, but it transforms under the product of two SUN gauge groups corresponding to the source and target of this arrow. Okay? So it transforms in the bifundamental representation. So you have and these diagonal arrows Phil asked about. It's just some matter field transforming under this gauge group here and this gauge group here. And so these gauge groups are located on this plane R245 direction, and then you can label them by two integers L and M, and you can imagine that that gauge group actually arises from part of D5 brain, which is diced by NS5 brain, located at this, containing this integer point. So, and then whole thing, actually, if you look at the setup, then there was 8-9 plane as well, and whole configuration is invariant under the rotational symmetry of R2 8-9 direction. And that rotational symmetry turns into what's called the U1R symmetry in the four-dimensional gauge theory. Right? So you get this kind of pattern, this kind of graph, which actually extends indefinitely. Right? So it's an infinite graph. I only shows you a small portion of that infinite graph. But this looks like some kind of lattice, infinite lattice. Okay? And this lattice has a unit cell, which is just a simple triangle of arrows. If you repeat this triangle many times in the horizontal direction and vertical direction, you get this kind of two-dimensional graph covering the entire plane. So this is a unit cell of this graph. And this unit cell, what is this? This just is a theory, four-dimensional theory, with only three matter field, three bifundamental chiral multiplets. It's a very, very simple theory. But from this simple theory, you can glue them to construct more complicated theory. Yep. No, so you have these 5 brains, and NS5 brains like chop them into like square pieces, and you consider strings ending on different pieces of D5 brains, different square like pieces of D5 brains, and they become these chiral multiplets. So these U1 flavor symmetries. Where did they come from? That's a good question. I don't remember. Yeah, I have to recall, but I can't recall right now. Yeah. Right. I think UN. So right, each one has UN, but somehow U1 part is not going to be gauged. Is that right? Maybe not. Maybe I'm wrong. Yeah. So yeah, I don't remember exactly where these U1 flavor symmetries come from, but it sounds like, yeah, probably they are the diagonal parts of these UN groups. Right. Any other questions? Now, so this is just so I just showed you a construction of this four-dimensional gauge theory, this encoded, described by this kind of planar quiver directed graph in terms of this brane configuration. But how is this related to Yang-Baxter equation? Okay. So now, this unit cell theory, the simple triangle of arrows, actually solves Yang-Baxter equation for, well, there are different versions of Yang-Baxter equation, but this one solves Yang-Baxter equation in the what's called interaction random phase 4. Okay. So here I have drawn the Yang-Baxter equation again. So you see 3 lines here, another 3 lines here, and they are related by the Yang-Baxter, that local move. And to around each intersection of 2 lines, you actually place 4 vertices of a quiver and then connect them by triangle arrow, which is the unit cell theory. Okay. So for this intersection of 2 lines, you draw triangle here. For this intersection, you draw another triangle of arrows here. For this intersection, you draw a triangle again, and you glue them. You glue 3 triangles together, and that's what you do here. So by circle vertex, circle node of this graph, it means that this symmetry group, so there's a SUN symmetry group which is gauged. The other vertices represent SUN symmetry groups which are not gauged. So gluing 2 theories corresponds to identifying SUN symmetry groups and gauge it. And that's how you glue 2 theories. So that's what I did for the left-hand side. On the right-hand side, you can do something similar. For each intersection of 2 lines, you draw a triangle of arrows like this, this, and this. And the claim is, all right, each side of this picture actually represents some kind of 4-dimensional theory which you can construct from 3 copies of this unit cell simple theory. And the claim is these 2 theories are actually dual in the infrared, meaning if you consider infrared effective theory, they are physically equivalent. So that's a claim, but how do you show that claim? All right, so if you go to this is about statement about infrared physics. So you can have to go to low energy limit. Now in the infrared at low energies, whenever you see a pair of arrows connecting to same 2 nodes and going in the opposite direction, you can actually, quantum correction can generate some mass term, which comes from actually quadratic superpotential. And these arrows, which are matter fields, they become massive and they are gone in the infrared. So which means that whenever you see this kind of pair of arrows going in the opposite directions, you can cancel them as long as you are focusing on infrared physics. So which means that you can cancel these pair of arrows here. Okay? And then if you compare the left-hand side and right-hand side, you see same arrows here and here, and here and here. You can actually similarly cancel them. And these, all right, so when you have 2 bifundamental chiral multiplets like this, you can write down superpotential W, which is this multiplet times this multiplet, and that gives them mass. And in the infrared, they are gone. Okay. Thank you for your question. So if you cancel these arrows, and then you can actually move some arrows from left to right using this relation again, then you end up getting this picture. And this picture is actually a very well-known picture because 2 sides of this equality, again, they describe 2 gauge theories, and they are related by something called Zeiberg duality. So it's an infrared duality. Okay. So Yang-Baxter equation is a consequence of well-known infrared duality between 2 4-dimensional gauge theories with SUN gauge groups. Now, what's great about this gauge YV correspondence is that it's a statement about 2 theories, not about 2 quantities. Okay? two theories go to the same effective theory at low energies. So if you calculate any physical quantity at low energies on two sides, they are necessarily equal. So one example is something called supersymmetric index, say on S1 times S3. You can place these four-dimensional series on S1 times S3. Well, this is a quantity you can calculate at ultraviolet, but it's known to be invariant on the renormalization group law. So you can calculate, and so if you calculate this index on the left-hand side, this theory index on the right-hand side, then they are going to be equal because these two are infrared dual theories. Now, once you do that, you calculate this quantity. So then this becomes an equation between numbers. And that will produce an ordinary solution of Yang-Baxter equation in the sense that these solutions are just numbers. So this HYB promotes Yang-Baxter equation from equation between some numbers, like R matrices, to duality between theories. Okay? And what's great, well, I shouldn't be spending so much time on this, but what's great is that you can calculate different quantities. You can replace S3 by, say, length space or some other spaces, cipher spaces, and you can calculate index on different manifolds, and they produce different solutions to the Yang-Baxter equation. So which was great. Now, here I try to explain why this construction produces solution to the Yang-Baxter equation. I try to do that. Only probably few understand this. But if you look at this configuration, now I replace the four-dimensional spacetime by S1 times S3 because eventually you want to calculate some quantity like supersymmetric index on S1 times S3. But then otherwise the configuration is the same. Now, actually, well, you can further generalize this 10-dimensional spacetime to this kind of spacetime where M curly M is four-dimensional manifold, Hermitian manifold, and then 10-dimensional spacetime is taken to be this. Km is the determinant line bundle, okay? And the cotangent bundle for some surface sigma. Sigma is any surface. And then if the phi brane wraps on the zero section of this bundle, then you can actually analyze and show that this produces something called a six-dimensional theory, which is holomorphic on this Hermitian surface M, but topological on this topological surface sigma. And so, yeah, I'll talk about it later. Not later, but after the talk. It's not so important, but there's one presentation. This is a topological equivalence. But anyway, so the point is you get six-dimensional theory, which is partly holomorphic, partly topological, and then you have S1 now. You can T-dualize everything and then lift everything to what's called M theory, and then you get M theory circle. But the important point here is that on M theory circle, these branes, NS5 branes, now become M5 branes. They can be separated. So at the end of the day, what's important is that you get some topological theory on sigma. So here sigma, you can think of it as just a plane. Okay. On sigma, which is 4-5 direction, these NS5 branes intersect along lines. So you have topological plane and you have lines, and theory is topological in this direction. You can move lines around, and that allows you to try to perform this Yang-Baxter local move. But furthermore, these lines are in M theory separated in this extra direction. So when you try to do this Yang-Baxter move, there is a singular point where three lines intersect at one point, but secretly they are separated in the M-theory circle, so nothing singular, no phase transition occurs in Yang-Baxter phase. So this is the bottom line is the structure of topological quantum field theory plus line defects plus this extra direction, hidden extra direction, which emerges in M-theory, actually leads to Yang-Baxter equation. So this is like a physical explanation for why you expect to get Yang-Baxter equation. But now, so this is all known from like 10 years and more ago. Now, I want to promote everything from Yang-Baxter equation to Tetrahedron equation. How do we do that? There's actually three-dimensional version of brain box model. Here, it was two-dimensional version in the sense that you had a two-dimensional square lattice structure, but there's a three-dimensional version, which is introduced by these people. So now, construction is pretty similar, but you use type 2B, instead of type 2B, type 2A string theory. So instead of D5 brains, you consider a stack of D4 brains, and they extend especially in R3, which is X2, 3, 4 direction. So you have R3 in 10-dimensional space-time, D4s fill that direction. But now you can introduce three different kinds of NS5 brains going, which is orthogonal to X direction, Y direction, Z direction. Okay, so you have three-dimensional space, and there are these NS5 brains, and they make a cubic lattice. Okay, so you can do everything you did in the previous case and try to calculate some things, and you would get solution of the Tetrahedron equation. So that's the expectation. So now, in this case, you have R201 direction, which is common among these supports of all of these brains, and you actually get a two-dimensional supersymmetric gauge theory emerging in this direction. It turns out to be 0,2 supersymmetric theory, which is described again by a quiver diagram, but now quiver is three-dimensional. Okay? So it looks a little bit more complicated, but you get this kind of infinite quiver in this R3 direction. But now, so let me quickly go over the meaning of these symbols. So again, each vertex of this quiver graph, represents gauge group, but now it's UN gauge group. And now there are two different kinds of arrows. Solid arrow represents bifundamental chiral multiplet, but in two-dimensional n equals 0,2 supersymmetry case, there's another kind of multiplet called Fermi multiplet, and I represent bifundamental Fermi multiplet by dashed arrows. So these are dashed or dotted arrows. So these red arrows represent another kind of multiplet. Now, so each gauge group is located at integral point in this R3 space. Right? So that you can think of it as coming from motion of piece of D4 brains, which contains this integral point. And again, there's a U1R symmetry coming from rotational symmetry in the 8-9 direction, and so on and so forth. But now it's pretty crazy, right? The quiver. But if you look at what the unit cell is, you realize it's just this one. This is a relatively simple theory, although it's much more complicated than before. So this is you have a theory with 1, 2, 3, 4 bifundamental chiral multiplets plus 1, 2, 3 bifundamental Fermi multiplets. You can glue this infinitely many copies of this simple theory in 3 directions, and you obtain this infinite quiver. And I can do the same argument as before and then argue that this theory, unit cell theory, should satisfy the Tetrahedron equation. The argument, yep. Yes, I will talk about it. It's one of the points I had to suffer a lot about. the not abelian part is cancelled, but the abelian part is not. Okay, so I will talk about it. So that's a good point. But anyway, so, and then this is a slide which shows you that actually there's exactly the same structure of TQFT and extra dimension as well. So now the starting point is type 2A theory, so it's simple to lift everything to M theory. And then there's M theory circle. D4 branes become M5 branes, which wraps the M theory circle. S5 branes become M5 branes. They are supported at points. Okay. Now, if you look at this direction, each of these M5 branes, the last three M5 branes, are like surfaces in R3. And then you can argue that this configuration gives you some topological three-dimensional theory on R3. So if you only focus on R3 direction, you realize that you get topological theory with topological surface defects, which are actually separated in this extra direction. And then you can imagine considering 4 intersecting surfaces and move them around using topological invariance, and then you go from the left-hand side to the right-hand side of the tetrahedron equation. Nothing singular should happen because they are separated in the 10 direction, x10 direction. So I thought back in the day, so that was 2015, this argument is solid. So this unit cell theory should satisfy the tetrahedron equation. So that was the expectation. But if you actually plug that into the tetrahedron equation, you realize that it doesn't satisfy the tetrahedron equation. So I was really puzzled by this. So I recently came back to this question and realized that there's a way to make it work. I don't know why it works, but it works. So I'm going to explain how to fix this in the last 10 minutes or so. Okay? So it's very stupid but simple. Simple and stupid, but I don't know why this works, but it does. So unit cell. So if you think about unit cell of some crystal system, the choice of unit cell is not unique. And then this is a unit cell, I told you, right? But you can actually take unit cell to be slanted in one direction by one unit. Instead of taking this box here as a unit cell, you can take this slanted cube as a unit cell. You can still glue them. In the 2D case, I didn't probably you are talking about Yang-Baxter equation, that diagram. Then that looks like slanted because lines are not orthogonal. Yeah, but I'm talking about cubic lattice. Everything is orthogonal, 90 degrees, regular cubic lattice. And then naturally, you would like to take the unit cell to be also regular cube, but that's not the right choice if you want to get a solution of the tetrahedron equation. Yeah. Yeah. So that diagonal arrow actually is there to begin with in the square lattice. You have a square lattice, but then there's a diagonal arrow. There are diagonal arrows in one direction, but not the other direction. So there's this asymmetry. Yeah, okay, so I can explain that later. But yeah, then I realized somehow you take a different unit cell, which actually by some coordinate transformation, which I write down here, is equivalent to this configuration. Now, if you take this as a unit cell, somehow this solves the tetrahedron equation. Okay. So I call it oblique unit cell. This is again some kind of theory with 4 chiral multiplets, 3 Fermi multiplets. I denote it with this symbol, and then so it's basically many arrows, many multiplets. Each arrow has actually parameters. So STU are some parameters which represent degrees of freedom in the choice of charge assignment on the U1 OR stage. So these STU become something called spectral parameters, which I talked about at the beginning. So now you just take this, plug this into the tetrahedron equation, and the tetrahedron equation. So in the case of Yang-Baxter equation, I talked about the Yang-Baxter equation in the form of interaction around the face. That form. There is something similar tetrahedron equation in interaction around the cube form. So this is a very complicated picture. Each side is something called rhombic dodecahedron. And each of them is decomposed into 4 cubes, but in two different manners. So this equation says that you have rhombic dodecahedron, 2 different decompositions, and for each decomposition you have 4 cubes, and each cube actually represents the unit cell theory. Okay, and so you glue 4 unit cell theory in one way to form a very big theory. You glue 4 copies of unit cell theory in another way, you get another big 2-dimensional theory. And claim is they are infrared equivalent. Okay. So why this works, why they are dual, is that this, if you write this down explicitly and cancel some arrows by using some known relations, and then it reduces to some duality, which follows from something called 0-2 triality, which was found by Gade, Glukov, and Kucherov in 2013. So this is an explicit calculation, very simple. Now, which means that now we obtain this equality, the equivalence between 2 theories. Now, if you calculate some quantities which are in the infrared, like supersymmetric indices, they are called elliptic genera in 2-dimensional case, then they become ordinary solutions of the tetrahedron equation. But there's a caveat. Okay. Like function says, there's actually a gauge anomaly. So there's a U1 part of UN gauge groups. They are anomalous, and they have to be canceled. Usually, they are canceled by introducing more multiplets in determinant representations of the gauge group. Here, in the brain box model case, so there's a string theory construction. So up in the string theory setup, anomaly is already canceled, and he has written some nice papers on that. And so there are some anomaly cancellation mechanism which is implemented automatically by string theory construction, and everything should be consistent. But the only thing is, I don't know how to calculate supersymmetric indices of theories with this anomaly cancellation mechanism implemented, which means that this prevents me from writing down explicit solutions, because I can't write down these indices explicitly. So even though I can say that when I obtain a solution in this way, I can't write it down. So what do? So there are 2 ways out, okay? 2 ways to move forward. One way is actually to reduce everything from 2D to 1D, because in 1D you don't have chiral anomalies. So somehow these anomalies are gone after you do dimension reduction to 1D. Then you can actually write down supersymmetric indices explicitly, and it's very easy because some people have done calculation for us before, and you can write down what Boltzmann weights we should assign to these arrows. It's a very simple Boltzmann weight, and then there's some kind of integration measure for each gauge group, and here important thing is to each gauge group, each vertex of quiver, you obtain n tuple of continuous variables, which you have to integrate over around the circle later. Okay. So you get circle-valued spin variables for each vertex of this lattice. So that's one way to write down explicit solution. Another way is to remain in 2D, but change gauge groups from UNs to SO to Ns. And there is a version of triality which looks exactly almost identical to 0.2 case, which is found by Gukov, Pei, and Putrov. And you can instead use this gauge theory. Okay. There is also a string theory construction, apparently. And in this case, I could actually write down explicitly how to calculate the elliptic genus in a way which looks like partition function of a three-dimensional lattice model. And you can actually check that this formula really gives you a solution of the Tetrahedron equation. So I would like to conclude if you don't have any questions. Yes.
That the form one. I'm not sure whether this is related to the fact that the IRC model, when that is a wrong Victor definition for each cube, that is not a regular cube. Is it possible?
Frankly, I have no idea why it's changing this choice of unit cell from very natural choice to this less natural choice works. So yeah, it's a complete mystery to me. It might be that sorry, I have no idea actually. Yeah, well, we can discuss more, but yeah, I don't have really any good answer on that point. So so let me conclude and give you some outlook. This is just one page. So one pressing question, at least to me, is how to write down the elliptic genera, which are supersymmetric indices of the original brain box model for two-dimensional 0.2 supersymmetry with all gauge anomalies cancelled. That should give you some kind of solutions of tetrahedron equation written in terms of theta functions. I think that's going to be interesting. I would like to understand this one. But second might be more fruitful. So there is something, brain box model is just one special case of much more general class of brain construction, which are known as brain brick models, introduced and studied by Franklin and others. So, so there's something similar for gauge YB corresponds. I told you when I explained there that I only consider the simplest case of gauge YB corresponds. There are more general and more interesting cases. And there's something similar here for brain box model. Brain box model is just one simplest case of these more general brain brick models, and I expect that you can construct more interesting solutions of the tetrahedron equation by considering more general brain construction. Another interesting question would be, so all the models I explained to you, I obtained in this way, have continuous spin variables, but it might be interesting to ask whether there are some limit in which these continuous spin variables reduce to discrete spin variables. Again, in the case of gauge YB corresponds, there is such a limit. And although gauge YB corresponds gives you spin models with continuous spin variables, by taking some root of unity limit, spin variables localized to discrete values, and then you obtain something like Ising model. So you obtain very many known models with discrete spin variables from single continuous spin variable model. So I would be very happy if I can get something like Ising model in 3D in this way. That should be very interesting. And another point is, here I explained that this tetrahedron equation becomes duality between two-dimensional series, but it's part of triality. So there is the third theory. The role of that third theory is completely mysterious to me. I don't know why it's there to begin with in this context. So I don't know what is it doing there? So that's a question I would like to ask. And the next point. So at the beginning, I mentioned that there is a construction of solutions of the Tetrahedron equation using class algebras. And then there's another construction using triality of 2D gauge theories. So is there any relation between them? There may or may not. I don't have any idea. And finally, here I introduce solutions of the Tetrahedron equation, which means that I have defined three-dimensional integrable lattice models. But then I just defined the models. So how to calculate partition functions using integrability. So that's a question I would like to leave to mathematical physicists, which I don't consider myself as part. Thank you.